Good morning, all of you. My screen is visible. Anybody? Anybody is there?
Yes, sir.
Yeah. See that previous class we observed single phase midpoint full wave controlled rectifier with R load and RL load. Now suppose if you connect with freewheeling diode, so you can see that waveforms also. Previously we know the I am drawing directly output voltage waveform. This is the R load, like this. This is the output voltage waveform for R load. Similarly, for RL load, we notice the different. This one is a something discontinuous mode of operation. The next cycle is going to be repeated, and then another one is a continuous mode of operation. And what will happen? It will continue to conduct and so on. So that shows, we can see that there is a negative voltage will be present in the case of RL load. So RL load, whether it is a continuous mode or a discontinuous mode, that decided by the inductor value firing angle and all. If inductor value is large, then what will happen? It will be as a continuous mode of operation. If inductor value is small, then it is a discontinuous mode of operation. Now, if alpha is less than 90 degree, you can see that this is the positive, more positive. This is the less negative. Then if you take average of this, will give as a positive. That is the case of alpha less than 90 degree. And if you try to draw alpha more than 90 degree for continuous mode, so we will get the waveform will be like this. So this is the case of same RL load only. This one is alpha less than 90 degrees, and this is the alpha greater than 90 degrees. Then what is the difference you can notice here? During this period is a less positive, and this period is a more negative. And if I take average of this, what will happen? Will give as a negative voltage. So always current is positive. If you draw the current waveform, it will give like this. It will rise up to pi and then it will decrease. This is the current waveform. So current is always positive, but voltage is always some portion is positive and some portion is negative. That depends on the alpha value, the duration. Now if alpha is more than 90 degrees, then obviously average will be negative, power is negative, then it acts as an inversion mode of operation. So that's what we noticed so far. To avoid the negative conduction, as we observed in the previous class, first class of this unit, freewheeling diode you can connect across the load. If I connect one freewheeling diode across the load, automatically negative conduction is going to be suppressed. So now we can see here what will happen. There is a inductor and then resistor. Now we'll see the operation during positive half cycle. This is plus, this is minus. Then current will pass like this. T1, it goes to R, then L to the neutral. Let it be as a O point or N point or whatever. Now the inductor will start charging with this direction. And while it is reaches to the pi, natural pi, suppose if it is the supply will be like this, and now at an angle of alpha you fire the device, it reaches to the pi, and because of this inductor, what will happen? This polarities will be reversed. now it will become plus. Then whatever energy stored in this inductor, that is going to be dissipated. Now you can see this one is a plus, this is a minus. Then what will happen? Plus is connected to anode of the diode, minus is connected to cathode of the diode. Then diode will be forward bias, it starts conducting. Then whatever energy stored in an inductor, that energy is going to be dissipated through this path. Now you can see whatever energy stored in an inductor, that is going to be dissipated through inductor, freewheeling diode, and then resistor. So gradually energy is going to be dissipated. Finally, once the energy is completely dissipated, then no current pass through the diode will be open. So during that instant, so what that instant we started at alpha and then ended at pi. Actually, if it is inductive load, it has to come like this. But now, because of this, what I call it as uh, diode, this will be short circuited. Then what will happen? This will become 0. But what is the current waveform? If you see the current waveform for with freewheeling diode, it rises, then it is carried by the diode. This portion carried by the freewheeling diode and this portion carried by the thyristor. So that is the difference. Earlier, that this portion also carried by the thyristor T1 only. But now this diode is forward bias across the load. Whatever energy stored in an inductor, that is going to be dissipated through freewheeling diode. That's why voltage will be 0. You don't get any negative voltage. This portion will be absent. Now we can see the difference. Earlier waveform, there is a negative voltage will be present, and that's why average output voltage will be decreases. But now what will happen? Because of the freewheeling diode, once it reaches to the pi, then automatically freewheeling diode will be forward bias, and then what will happen? Energy stored in inductor is going to be dissipated through freewheeling diode, and therefore voltage will be 0. Why voltage is 0? Because this will be short circuited. This is on in the sense directly short circuit the load terminals, voltage will be 0, but current is freewheels through that loop. That's why we are getting start with alpha and then pi plus alpha. So that will be as a current waveform in this, and voltage waveform exactly same as that of R load now, because R load automatically thyristor T1 is going to be turned off at pi, but only RL load it will continue to conduct some more time. That is the difference. And now same thing we will see the waveforms for your reference. That's all. Nothing is there, just supply and then output voltage waveform. Whenever if we give the firing pulse, it starts conducting and get it up to the pi. Then it will be pi plus alpha, that will be instant is 0, because during this instant current is going to be freewheels. So now we can see this if you draw current waveform. This is not this is a voltage waveform, same thing it run. Then current waveform it will rises, then decreases like this, and then it goes like this. So this portion carried by the freewheeling diode, this portion carried by the thyristor. But current is not 0. Why current is not 0? There is a energy stored in inductor that is going to be dissipated through diode. That's why current will flows through diode but not through thyristor. So that's why when there is no current through thyristor, thyristor will be turned off at pi. That is the reason this same shaded portion I drawn here. This is not a current. You just make it as a voltage waveform, and then current waveform, this red line. So this is the way. Now what is the expression we can derive? I want to derive VDC. It is same as that of R load, because 2 pulses in a one full cycle, then 2 by 2 pi and just integrate it. Alpha to pi, output is Vm sine omega t d omega t. So this is just like R load. So now what will happen? It is a Vm by pi. Integral sign will give minus cos omega t. So limits are alpha to pi. So this is nothing but a Vm by pi into 1 plus cos alpha. That's all. So this is the expression for now. We can observe that midpoint full wave control rectifier with different loads. R load, RL load, and RL load, and with freewheeling load and all. Now we'll move on to single phase fully controlled bridge rectifier. So what is the difference between these two things? Whereas in case of midpoint converter, we required as a transformer. This one, this transformer is required. So that is additional burden. We need to isolate that power circuit, and this will be there is a isolation is required. And here we can see that this transformer will give more losses. So and also midpoint we required. So secondary must be as a midpoint. So to overcome this drawback, we are going with the bridge type controller. But remember one thing, waveforms, average expressions, and current expressions, RMS, everything is same. Bridge control rectifier will not give more than this voltage. Whatever voltage will give the midpoint converter, same voltage will give. Waveforms also same, but only the different is what? Devices are different. Here the conduction thyristor T1 alone is conducting to get this pulse, no? So whereas if we go to bridge type, two devices are required to get this. And similarly, to get this, we require only T2. One device is sufficient. But whereas bridge type, two devices are required. And the thing is, we don't require this transformer. To remove the transformer, we are going with the bridge type configuration, but average expressions, everything, magnitude of that output and this output is exactly same. It won't be differ anything. Only intention is here to remove the transformer. That is only the purpose. Now we can see bridge type rectifier. This is a full control rectifier. So what is meaning of fully controlled rectifier? I told this is a two pulse converter. Half wave is one pulse converter. Full wave is a two pulse converter. Now whether it is a R load or RL load or RLE load or whatever the load you can connect, or a semi converter or a full converter, both will give as a two pulse converter. This must be remember. It is also called as a B2 converter, bridge type two pulse converter. So that means we can see that how the output is going to be. Once if you are aware the previous explanation and all, it is very easy. Again same logic during positive half cycle and during negative half cycle. So during positive half cycle this is plus and this is a minus. Then what is the current directions and all? You can see that it goes to the T1, then R, then T2 to out during positive cycle, because you try to identify what are the devices are forward bias when supply is positive half cycle. Then this will be forward bias, this will be forward bias during positive half cycle, and during negative half cycle this is minus, this is plus. And what will happen? The plus terminal is connected here, this is a plus terminal and this is a minus terminal. What will happen? Minus is connected to anode of T1, it is a reverse bias. Same minus is connected to cathode of T4, it is a forward bias. Therefore T4 will be forward bias. Now plus is connected to anode of T3, it will be forward bias. Plus is connected to cathode of T2, it is a reverse bias. That means with that, similarly positive cycle means this is plus, this is minus. Same logic you can apply. Plus is connected to here, it will be forward. Minus is connected to T2, it will be forward bias. It will be in the case of minus, no, this will be forward bias. Now like that, first you identify for positive half cycle what are the devices? T1 and T2 will be the forward bias. For negative half cycle there is a T3 and T4 is a forward bias. So that's it. Once if you know the supply, at what instant what will happen, we can easily draw the waveforms. It is very freely you can draw the waveforms. Don't be confused. It may be different loads and different waveforms are there, but once if you understand the logic, then you can easily do the magic. It is nothing, just you give the positive pulse. Whenever positive half cycle is there, you can give the pulse for positive devices. That means T1, and here also positive. You can give pulse at an angle of alpha. For negative half cycle, you can give at an angle of pi plus alpha something pulse here. So now 0 alpha. This is a pi. Then 2 pi. This is a supply I am writing. 2 pi, 3 pi, and so on. And 2 pulse converter, I must give the 2 firing pulses. One is for T1 and T2, both same pulse only. Why it is T1, T2? Because these two are forward biased during positive half cycle. Both has to be turn on at the same time, turn off at the same time. That's why I have to give the pulse to this T1 and T2. And similarly, this is for same negative half cycle T3 and T4, both has to be fired at the same time. So T1, T2 and then T3, T4. So this way first you have to give the firing pulses. Next what? I have to draw the output voltage. How will you draw the voltage waveform? You can see this. Current will start like this. It goes to T1 and then it goes to the R load, then T2 to out. What is our output? Same as input only, no? So what is your input? AC supply. You just draw that. Once it reaches to pi, what will happen? Device will be turned on. And again, during negative half cycle means T1, T2 will be off at pi due to natural commutation. You make it that sentence due to natural commutation, the resistor 1 and 2 will be turned off. It started at alpha, ended at pi. Then pi to pi plus alpha, what will happen? No firing pulse to any of the device from pi to pi plus alpha. You can see only at pi plus alpha pulses are there for T3, T4. That's why from pi to pi plus alpha, no devices will conduct. That is the reason, like 0 to alpha, no device is conducting. No, if no device is conducting, output is 0. 0 to alpha, no device. Again pi to pi plus alpha, no device. And then again what will happen? You can see here at pi plus alpha, there is a pulse to Ig3 and Ig4, means T3 and T4. Then this is a negative half cycle, minus and plus. What is the current direction? This one is plus, no? It start T3, then it goes to the R load, then goes to T4 to out. That means we started at plus, it goes like this, then what is your output voltage? Same as again source. Then what is source? You just draw the source voltage. That's it. And again, once it reaches to the 2 pi, what will happen? Supply voltage 0 and current also 0. Then automatically thyristor is going to be turn off. T3, T4 is going to be off. And then again positive half cycle started 2 pi onwards. But at 2 pi, no firing pulse. Then you have to wait up to 2 pi plus alpha. So at 2 pi plus alpha, you are giving pulse to the T1 and T2. Then T1, T2 will conduct. Then the output voltage will be the same as source. That's all the voltage waveform. And similarly, you want to draw the current waveform. It is just instead of make it this much magnitude, you can reduce some magnitude. This is the current waveform. Again, it's green. Same instant, same, everything is same. You can get the current waveform. So this is the fully controlled rectifier with R load. Now you can recall that midpoint R load also same waveforms. But only the thing is the conduction devices names are different. Here T3, T4 will conduct, and here T1, T2 will conduct. So like that you'll get the different devices conduction, but the you can see voltage waveform, current waveform is same. Then what I can do, our expression is same. So if expression voltage waveform is same, we can see that we can easily make it as a output voltage expression. How will you write the voltage expression now? For this, again 2 pulses in output, that is a 2 by 2 pi, and then you can make it as a V out or VDC for R load. Now that is equal 2 by 2 pi in the sense 1 by pi integral alpha to pi Vm sin omega t. So that means you'll get same magnitude. So this is the case for R load. Similarly, we'll see the other loads also. Now we can say it is a one quadrant converter. Why I call it as one quadrant converter? As we noticed it, the voltage waveform and current waveform both are in positive. So positive voltage, positive current, power is positive, power flows from source to the load. That's why represented as a first quadrant converter for R load only. Same controller, if I use RL load, you will get as a two quadrant converter, first and fourth. Now this is the pulses we have to give for positive half cycle, and for negative half cycle you have to give for the T3, T4. That's why I mentioned Ig1 and Ig2 for the T1, T2, and Ig3, Ig4 for the T3, T4, and then once T1, T2 conducting, same as source and load voltage and load currents be drawn, and voltage across the device, it is exact same logic. You can see wherever I specify T1, T2, from here T1, T2, here T1, T2. That means during that instant you make it short, just make it 0, and rest portions as usually. This is the rest portion 0 to alpha, and from pi to it is device turn off at pi now. From this point to up to 2 pi plus alpha, same as source voltage. Only conduction instance you make it as a 0, rest portion you redraw from the source. You just see the source and rewrite. And similarly for negative, I mean T3, T4 also, it is whatever written path will be there, no? That you can redraw as such. Once device is conducting, make it 0, here also same logic. And if not conducting, whatever the source is available, you make it. So this is the R load. Now if you do the simulation, you will get same results. That we can do it already, same experiment completed, and verify the R load and RL load, all these things. Now the average expression, all these things I derived. Now just V out is equal to Vm by pi into 1 plus cos alpha. RMS again same. Now some books they represent like this, but anyhow same as previous. VRMS, that is equal to Vm alone, you take it common, because previous derivation this will make it inside. Then what I can write, Vm into pi minus alpha. Then if you go inside root 2 pi, that is a 2 pi, and plus, then same thing you multiply here, 2 to get 4 sine 2 alpha by here 2 and 2, 4 pi whole power 1 by 2. That's all, same only. But some books they made it root 2 outside pi and all. We can do that way. Anything formula is same. Now, so this is the RMS, and peak inverse voltage is one different. In case of R load, there also same Vm only, but RL load case you'll get it as a 2 Vm in the midpoint case, total voltage applied across that, and here Vm only because it is a bridge type. And we'll see the RL load. So what is different R load and RL load? Very small different. Whatever waveform we are drawn for RL load in case of midpoint, same thing is going to be repeated. For rectification mode, as usual, alpha must be less than 90 degrees. This is the waveform for rectification, alpha less than 90 degrees. And then greater than 90 degree, what will happen? The positive will be less and negative will be more. Like this we'll get it. So this is the alpha, different alphas. Anyhow, I will show that waveforms also. Now, RL load fully controlled rectifier. It is important question. They may ask different way. One way is simply explain single phase full controlled bridge rectifier with RL load. Another question is explain single phase full control rectifier with the rectification mode of operation and inversion mode of operation. And third one is explain single phase full control rectifier with continuous mode and discontinuous mode of operation. And then another question, the same answer, explain line commutated inverter. That's it. So these are the different questions. Or you can say that explain two pulse converter with the RL load. In that case you can write even semi converter also. And here you can see line commutated inverter means same question. If alpha is greater than 90 degree, that act as a line commutated inverter. Normally inverter means what? It will convert DC to AC. But why I call it as line commutator? Here in the normal inverters, that is step inverters, we required forced commutation circuit. But whereas here we don't require any forced commutation circuit, but it will fed back source to the load, power fed back to the source. So that means whatever load power is there, DC, that is fed to the source. So that is converted to AC. That means DC to AC, it is an inverter. But why line commutator? Because to turn off the device we required as a same line supply. So that's why it is a line commutated inverter. So and that is one important question. Explain line commutated inverter. Same circuit, this circuit only, but only the thing is waveform you must draw greater than 90 degree. Only if alpha is greater than 90 degree only, power flows from load to the source. So because more duration negative voltage, less duration is a positive voltage, that is the reason. Now we can see the waveform. What is this rectification mode of operation? In a rectification mode of operation, alpha must be less than 90 degrees. So up to 90 degrees is fine. Exactly 90 degrees, average will be 0. Now we can see alpha less than 90 degrees, somewhere at 30 degree. I made a firing angle to Ig1 and Ig2. Similarly, at pi plus alpha, there is a Ig3 and Ig4. Once Ig1, I mean T1, T2 is conducting. What is your voltage? Same as the source voltage. Once it reaches to the pi, what will happen? Normally, supply is 0, load voltage also 0, current is there while it is conducting T1, T2, current is passing through the what inductor. So it will store energy plus and minus. But now because of this energy, the polarity EMF polarities will reverse the inductor, and now this will be minus and this will be plus. So once this polarities are reversed, same device is going to conduct some more time. So why that some more time? Because of energy stored in an inductor. So while it is dissipation, what will happen? This will be same negative. I mean because it is conducting, no, supply output is same as source, but source is negative after pi. How long it is conducting? Let it be large inductor, it will continue to conduct up to pi plus alpha. Once it reaches to pi plus alpha, next set of devices are forward bias, supply is negative, and then these devices are forward bias, then automatically T3, T4 is starts conducting. So now the same from pi plus alpha onwards, this will start conducting. The current will be from here onwards T3, T4 carry the current up to the 2 pi, then it is decreases. Again at 2 pi plus alpha it is rising. So like this, we can see that voltage and current waveforms, it is a continuous mode. If we take average, average is positive. It is very quite simple by seeing the waveform during this pi minus alpha instant. This you can see that pi minus alpha instant is greater than the alpha instant. So obviously will give more positive. And the current waveform source currents also, you can see that whenever you draw current from the source, then you draw it. Now here the current coming from the source, because T1, T2 is conducting. Here also current coming from the source T3, T4 is conducting like that. So from the source waveform you can write from alpha to pi plus alpha, draw the source current, and then pi plus alpha to 2 pi plus alpha source means negative voltage. So that will be as drawn from the source. So we can draw, make it as a, this is the waveform for current. And now Vt1, Vt2 as usual. Vt1 0 to alpha, it is not conducting. That's why they will give the voltage across that Vt1 and Vt2, and then alpha to pi plus alpha it is conducting. Then pi plus alpha to 2 pi plus alpha it is not conducting. Then it will be same as the source. Just reverse of that. So that will be wherever it is conducting. Now we can see that in the negative conduction, you can see this duration. You want to can write that instance which device is conducting. Here alpha to pi plus alpha T1 and T2. Then pi plus alpha to 2 pi plus alpha up to this, and from alpha to up to this, and here 3 and 4, and again 1 and 2. From this, what is we noticed with this portion, because it is a negative half cycle, it will be there, no, in this way. So this negative half cycle, who will conduct T3, T4. How long it will conduct? Up to pi plus alpha, no. So that means here is alpha. So that's the reason here the device will conduct 3 and 4. So like this is the instant the device is good. So 3 and 4 is conducting here. That's why I make it as a 0. But resistive load 3 and 4 will not conduct from 0 to alpha. Both devices are off. That's why we made it as same as like this. Same as source. It will get like this. But only the thing is here wherever the device is conducting, make it to 0. That is the case of now RL load. I made it alpha. This one is alpha less than 60 degrees. Or I mean less than 90 degrees. You make it whatever may be alpha. Alpha is equal to 60 degrees or 30 degrees or anything. This is the waveform. So one first question, explain the rectification mode of operation. Use this circuit, and then this is the waveform, and it will, you can show that average output voltage is positive and power is positive. Power flows from source to the load, and hence it is operating under rectification mode of operation. That's it. And similarly, if you do the simulation, we'll get like this. And then we will go for as a inversion mode of operation. Here the two things, inversion mode of operation or line commutated inverter. Separately sometimes they ask A bit or B bit, explain line commutated inverter alone. That means what? Circuit is same, but waveforms should not draw these waveforms. This waveforms is only rectification mode of operation, or I can say this is alpha is less than 90 degree. But our case is what? Inversion mode of operation. You must give more alpha. So therefore you can see I am giving alpha will be greater than 90 degrees. So let assume that alpha is equal to some value. Let it be 120 degrees. Anything greater than 90 degrees. Or alpha greater than 90. This way also you can mention it. But now what is observation from this? As usual, continuous mode of operation only. Let consider large inductor. It is giving as a continuous mode of operation. But where it will start is different. No, alpha, you can see here. Earlier we started here because alpha is 30 degree or 60. But now greater than 90 means you must show after peak. Whatever peaks will be there here. No, supply peaks. Supply peak means 90 degrees. But our intention is more than 90 degree. So somewhere you can put it after 90 degree. And you want to can draw the pulses also again. Anyhow it is drawn. This is for T1, T2, and then for negative this is the for T3 and T4. So like that you can provide as a firing pulses. Once you provide the firing pulses, start with the alpha and starts conducting. Then it reaches to the pi. At pi device will not turn off because of the inductor. It is continue to conduct in the same loop. That's why we are getting as a same as source voltage. How long? Because it is a continuous conduction, it goes up to the pi plus alpha. So therefore again at pi plus alpha, there is a T3, T4 is going to conduct. So pi plus alpha T3, T4 will conduct, then output is same as source, and again 2 pi plus alpha, and cycle is going to be repeated. And current waveform, we can notice that the small duration is charging. So that's why it will charge the current like this. And after that, gradually it is discharging. Because this duration will be more, the reason is alpha must be greater than 90 degrees. So then it is discharging slowly, and again it will charge, then discharging. So with this process, we can able to get the current waveform continuous mode. But you can see the both voltage and currents. If voltage is positive and the current is positive, then power is positive. But whereas here, if we take average, what will happen? This duration is a pi minus alpha, no? This one is pi and this is alpha. Then the pi minus alpha is less than alpha. What is our alpha? Let us assume that alpha is 120. Let consider alpha is 120 waveform, and then pi means 180 minus 120, that is less than 120. Alpha is 120, no? So this is equal to 60 degrees duration, we are getting only positive, but 120 degree duration we are getting negative. So if you take average, what will happen? It will give negative. So this line is a average line, the solid line. Then current is positive. So if we multiply this two thing, then what will happen? Average will give as a negative. So average negative means power negative, no? Power negative means that power flows from load to the source. Load is what? DC. Source is AC. Therefore, DC to AC, it is an inversion mode of operation, or also called as a inverter operation. So line commutated inverter. Why it is a line commutated? Because power, we make use of supply lines to turn off the device. We are not using any additional circuit. So this is very important question. Single phase fully controlled bridge rectifier with resistive load, okay, that is as usual of semi converter or midpoint converter. But whereas here full case what you call it as RL load, rectification mode and inversion mode of operation. So that's what we mentioned here. The rectification mode of operation, alpha is less than 90 degrees or 0 to 90, and then rest portion beyond 90 will give as a inversion mode of operation. Now we will see that in the case of discontinuous mode of operation. Anybody, what is the difference of continuous and discontinuous? Let now consider inductor is small. Then as per our previous waveforms only, what I can represent discontinuous, exactly remaining is same. Only thing is we started at alpha. Anywhere you can start, there is no issue in that. Let you can start somewhere alpha or less than 90 or greater than anything. In that it will continue to conduct up to beta, and then next set is going to be conduct. So this is a next thyristor. You can start here and it will continue to conduct up to beta, and then at pi plus alpha T3 T4 will conduct, then it will continue to conduct next beta, then T1 T2. So this is the different. Now we can see earlier what we noticed that he started at alpha, this is a pi, this crossing x is pi, this is a beta, and this one is a pi plus alpha, and so on. So now what is the difference? If the inductor is large, then this gap will continue to conduct up to pi plus alpha. This is what I shown you for the previous continuous mode of operation. But now because of the discontinuous mode of operation, that device will not conduct up to pi plus alpha, because it is insufficient energy stored in inductor, or you can say that small inductor, to dissipate it will take less time. Then if you draw the current waveform, then the different we can notice that current waveform case, You can see we started at alpha, current will start rising. How long? Up to pi, then it is decreasing to beta. Then beta to pi plus alpha, what will happen? No device will conduct. Again current is rising and decreasing. Then 0, then like this. So what is the gap you can see here? So we started at alpha, ended at beta, and now beta to pi plus alpha, no device is going to conduct, because we are giving firing pulses only at alpha, pi plus alpha, 2 pi plus alpha, 3 pi plus alpha, and so on. So that is the reason we can see that when you are not giving any firing pulses to particular instant, no device will conduct, because at any instant we required firing pulses. So in this context, but the device T1 T2 is turn off at beta, but again T3 T4 will fire only at pi plus alpha. That's the gap. You can see that here the gap beta to pi plus alpha, no device is conducting, that we call it as a discontinuous mode of operation. Now waveforms, everything is same, only the reason is because of the load inductor is small, then you can say that it will be become as a discontinuous mode of operation. Now that's we can see same thing I drawn here, the current waveform, voltage waveform, and then can see in the waveform I started at alpha. Here I started at alpha, then T1, T2 will conduct as usual, then it will continue to conduct up to beta. Earlier, if I say in the previous class also I told no, continuous mode and discontinuous mode means if beta is greater than pi plus alpha, or you can say that beta is equal to pi plus alpha, I can say it is a continuous, but beta is less than pi plus alpha, it is a discontinuous mode of operation. In that context, we can show that this gap must be as a discontinuous mode of operation. Now we started at alpha and ended at beta. Beta to pi plus alpha, you can show here is a beta, and nowhere the firing pulse is available. We are firing pulse is available only at pi plus alpha. So therefore beta to pi plus alpha, T1 T2 is off, T3 T4 is already off. Then during that instant no device is conducting, therefore output will be 0 and current also 0. That is the reason I can say by seeing the current waveform you can decide it is a continuous mode or a discontinuous mode, because the current is remains 0 some duration. That is the reason I call it as a discontinuous mode of operation. And whenever device is conducting, again same logic, here the device is conducting alpha to beta, you make it 0, rest you make it source. Whereas earlier voltage across the devices, what you will do, make it alpha to pi plus alpha, you make it 0. At pi plus alpha, it will be same as this. So that is the differences between continuous mode and discontinuous mode of operation. Now the waveform again same, you can make it that. And discontinuous mode of operation expression, what is the expression? You start with alpha, end with beta. If it is a continuous, start with alpha, end with pi plus alpha. That is the difference between continuous mode and discontinuous mode. And again same, this is very important graph. We can notice that this graph is similar to midpoint only. There also average expression, what you got at midpoint case, 2 Vm by pi into cos alpha. For continuous, 2 Vm by pi into cos alpha. Now also same. Now alpha is 0, 2 Vm by pi is maximum we are getting, and go on increasing the alpha, it will be gradually decreasing because alpha is varying, and once alpha reaches to 90 degrees, cos 90, that will be 0, and then total output will be 0, and if we increase beyond 90 degrees, then what will happen? This will be negative, and gradually it will develop negative. Once exactly reaches to the this point, this magnitude will be as a minus 2 Vm by pi. So from this it is very clear that this first quadrant operation, this is a fourth quadrant operation, or you can say that alpha less than or equal to 90 or less than 90, exactly 90 means it will be 0 this point, and here is alpha greater than 90, we can make it as a negative. So this is the relation for average output voltage versus firing angle. And now we can see this RLE load. What is the difference of RLE load? Now it acts as a motor only. Output load side, it is a motor. Now there is a gap, exact waveforms, nothing else. This is a discontinuous mode of operation. Whatever I shown this waveform here, this and that is same. Only different is this thing. You can see here I made it 0. Why I made it 0? No device is conducting. So load and source are isolated because T1, T2 is off, T3, T4 is off. So both are off. That's why I make it 0 there. But now what I will do, even though this set is open, left hand side all the devices are open, I want to measure at load side. No? So here I want to measure what is the output. So this point, if I connect as some battery or voltage source, that much voltage will be present here. Instead of make it 0, you make it something magnitude. So that's all the your waveform. You can make it wherever it will be 0, that you can keep it some magnitude, and that will be as a like this. So that's it. That's what I drawn here. You can see that only during that instant, earlier it was 0. Here normally I want to make it 0 like this, but now you make it something magnitude whatever you placed in this. That's it. So that is only different. Every waveform is remain same. That's why don't confuse, for each point there is a waveform, but what you need to understand is what is the difference between R load and RL load and RLE load and RL with freewheeling, like that. So only the difference is also fixed for all the controllers. One thing is, I will say that first R load, start with alpha, end with pi. That's it. And then RL load, start with alpha, end with pi plus alpha for continuous, or beta for discontinuous. That's it. And RLE load, that gap, wherever gap is there, you make it as a source voltage. I mean, whatever battery voltage is there, that magnitude will be remains there in the load side. And RL with freewheeling diode, it won't get negative. Start with alpha and with pi. That's all the fixed logic for all the controllers with different loads. And now for continuous case, it won't be happen anything. Anyhow, it will be going to conduct. This will be start with alpha and then pi plus alpha and so on. But alpha will be always between theta 1 and theta 2. This I call it as a theta, this one point I call it as a theta 1. This point I call it as a theta 2. I already explained why greater than theta 1 only are to give the firing pulse. Before theta 1, the devices are reverse bias. And after theta 2, also devices are reverse bias. That's why firing angle limitation here between theta 1 and theta 2. The remaining waveforms continuous, exactly same as the previous RL load waveforms only. Now we'll see the semi-converter. So what is the semi-converter? It is very simple logic. I can say that just lower group devices are replaced with diodes. Earlier, you can see the circuit. Now again same logic, everything is same. You can see that for a full controller, what I used, this is the full controller. Only names are different, T1, T2, T3, T4 like that. But now, if I keep lower group devices are the all the devices in a circuit is a thyristor, that is a full control. And upper group devices are thyristor, lower group devices are the diodes, then it is a semi converter. Another name, this is upper group device, this is a lower group device. So another name for this I call it as a, what I can say that it is a semi converter, or another name for that is a half controlled. So because semi or half control both are same, but half wave is different. Now the waveforms everyone can write without seeing this. Start with alpha, I mean we are giving firing pulse to the thyristor 1 alone, and anyhow other device is a diode. Current start from L, it goes to T1, then R, then goes to the D1 to out. Then output is same as source. Now exactly same, nothing, even if it repeats many number of time, but waveforms are same. So now we start with alpha and then end with pi. Right? Due to natural commutation, T1, T2 will, T1, D1 will be turn off. Again at pi plus alpha only we are giving pulse to the T2. That's all the output voltage waveform. So now what we can make it is, we'll start with alpha, and this is a pi, then pi plus alpha, and then 2 pi. Now device conductions are different. You just may find the what are the devices from alpha to pi. So alpha, there is a T1 and D1 will conduct, and here no device will conduct because due to natural commutation it will be open, and no pulse is available from pi onwards, pi to pi plus alpha. At pi plus alpha only pulse is there. Then here who will fire? T2 will fire, then D2 will fire. Whereas here T1, D1 will fire during this instant T1, D1. That's all. Now the waveform is similar to that of fully controlled rectifier with R load. Output also same. So full control rectifier R load, semi converter R load waveforms are same. Only the device names are different. There we have T1, T2 will conduct first positive cycle. Then the T3, T4 will conduct next of cycle. But whereas here T1, D1 will conduct, then T2, D2 will conduct. This is a symmetrical configuration. That difference will be there only for RL load. For R load case, you can see that symmetrical configuration or asymmetrical configuration, both are same. The arrangement of the devices are different. Then output voltage, waveform, everything is same. Don't confuse anything. Only the different is the device conduction durations are different. If it is all the devices, T1 is conducting same duration, T2, D2, D1, all the things are same durations, then it will call it as a symmetrical conduction configuration. And then asymmetrical configuration means any particular instant, you can see that RL load case I'm telling, the T1 is durations different, diode durations are different. That's why it is a asymmetrical configuration. But whereas R load case, you can see the waveform is same. If I use symmetrical configuration or asymmetrical, you can see now T1 and it goes to the D2 to conduct, and again for negative off cycle who will conduct? D1, then it goes to T2 to out. So for both instants, the devices are same durations. So that is the reason I can say it is a both is same for resistive load, waveform is same whatever I drawn. I will show here. This is the waveform exactly same. I am giving firing pulses to, because here only two thyristors T1 and T2, whereas there will be the two different thyristors. Now we can make it, here is only T1 will fire. Pulse is available for positive cycle, it will take it T1, and negative cycle this goes to the T2, and T1, T2 will conduct, T1, D1. These are the device diagonal elements will conduct, that's it, for positive cycle as well as the negative cycle. And now expression again same as the fully controlled rectifier only. But now the question will arise, why we required semi converter if the full controller R load and this is same. So for semi converter cost is less. Diodes, two diodes are required and two thyristors. But whereas full controller all four thyristors are required. So whenever you require only motoring operation, you don't go for full. You can make use of semi converter or a half controlled. The reason is half controlled is cheaper than the full control, but our intention to operate the device or application is only the motoring operation. That is the reason you make use of devices in the you can say that the what we call it a first quadrant operation, use only the semi converter motoring operation. But full controller also will give the first quadrant, but we don't require braking operation. At that condition only you can use as a semi converter. That's why Vm by pi into 1 plus cos alpha here and there is same, and rest of the derivation also same. Now once the voltage waveform is same, remaining wave expressions are same. Whether it is a RMS or average, everything is same. I told no Vm into pi minus alpha by 2 pi and sine 2 alpha by 4 pi whole power 1 by 2. That is the RMS. So now we can make use of asymmetrical configuration. Again, the things are same. For R load, I'm telling both are same. Only device can see the T1, D1 is conducting. Here you make it as a D1. The convenience, same notation you can follow. And here you can use T2 name, device name. So now the conduction you can see T1, it goes to the D1 to out, or if you start with D2 and it goes to out. So that way, whatever you can do that, the device conduction here T1 is there only once, and here T2 is once. So this total duration it is count by T1, and D1 also conducting only this duration, and D2 only this duration. Now how many degrees it is conducting? You can see that if I want to know what is the how many degrees T1 is conducting, total start with alpha and with pi, no? So the gap is what? Pi minus alpha. Pi minus alpha, T1 is conducting. D1 also conducting pi minus alpha. And then same, you can see here, this one will be as a pi plus alpha starting, and end with will be 2 pi. So now what is the difference? 2 pi minus pi plus alpha. So then what you can get it? Pi minus alpha gap. So pi minus alpha. So therefore T2 also conducting pi minus alpha duration, and then what is this D2? D2 also conducting pi minus alpha. So that much durations are same. So all the devices conduction durations are same. That's why we call it as a symmetrical configuration. And here also in asymmetrical case also all the durations are same for resistive load. That is the reason for in the case of R load, symmetrical or asymmetrical, no matter, that will be as the same durations it is going to conduct. But the thing is, if you go for RL load case, symmetrical case diodes are different, and durations, and then thyristor durations are different. That is the gap, or you can say that. That's the only the reason we call it as asymmetrical configuration, because there is a even if you avoid that, you can directly use one diode here also is fine. We don't matter of symmetrical or asymmetrical. Directly if you use the diode, then the waveforms wherever lower group devices are conducting, in the diode case, that will be directly freewheeling diode will conduct. Now you can see operation for this is just for simulation. And now for RL load. What is the RL load waveforms? You can notice that while after pi you are not getting negative, when in the case of full controller we are getting as a negative, but now we are not getting as a negative voltage even after pi. The reason is, you can see that it is very straightforward, because of the diodes, lower group diodes are there. Now we can start keenly observe. During positive half cycle it will goes to conducting T1, then goes to R, then R and L, it goes to D1 to out. Then inductor will store energy like this, that you can remember. So that's why output will be same as this, that will be up to alpha is no doubt, it will get it like this. But now after that what will happen? You can see that it is already stored plus and minus during positive half cycle. Now it will become, this one is a negative and next one will be as a plus. This is the plus and minus. Now after pi, which device is going to conduct? After pi, lower group device is a forward bias. Now we can see that D2 will be the forward bias. Now reason is plus is connected to anode, this one, and minus is already T1 is conducting, it is connected to cathode. So therefore what will happen? D2 is a forward bias. So during positive half cycle T1 D1 is conducting, but once it reaches at pi, this inductor polarities are reversed and minus is directly connected, because it is T1 is already on, no? So minus is connected to this point and plus is connected to anode of D2. Therefore D2 will be forward bias. If D2 is forward bias, T1 is forward bias, this total leg is conducting now. If this leg is conducting, then where it is connecting that leg? This leg is directly connected to the load. One point there, another point is here. Then the load terminals directly short circuited. Then whatever energy is stored in that, it is freewheels through this loop. What is this loop? Inductor R, then it goes to the D2, then T1, and like this. So energy will be gradually decreases. So that's why we can say that voltage will be 0. You are not getting any negative voltage because load is directly short circuited across this T1 and D2. That's why I mentioned this portion T1, D2 is conducting. Here normal case T1, D1, and once it reaches to the pi, energy dissipation is taking place, then the T1, D2 is going to conduct. That is the reason, even though if it is RL load, you are not getting any negative voltage. So that is the reason the semi-converter will be the first quadrant converter. It is a motoring operation alone. Whether you use R load or RL load or any load, you will get only motoring operation. And next one, suppose during negative off cycle, what will happen at this pi plus alpha, energy is completely dissipated. Again, this diode D2 will be reverse by, open. But now again negative off cycle D2 will be conducting. No, what will happen? Supply is negative. Supply is negative means this is plus, this is minus. Then the minus is connected to cathode. So diode D2 will remains in the on state. But what will happen? D2 T2 for thyristor firing pulse is available. Now the conduction will start like this. T2, it goes again same and then D2 to out. That's why T2 D2 will conduct. Now the polarities are plus and minus, it will charge. After that, once it reaches to the 2 pi, then what will happen? Polarities will reverse. What is polarities? This is minus, this is plus. So therefore, this is already conducting and plus is now connected to this point and minus is now connected to this point. Therefore, this leg will short circuited. Then what will happen? Once this leg is short circuited, again output voltage will be 0. So we are not getting any negative voltage like that. Every instant of time, one of the leg will act as a freewheeling diode. So therefore you never get as a negative voltage. So that is the reason you can say that this semi converter will give as a, will not give any negative voltage, will give only the first quadrant operation. Or if you are confusing how the devices are conducting, you can use directly like this in the circuit itself. Now it is very fine. You can see now. Operation is just simple. It goes T1 for positive off cycle, D1 to out. Now energy will store like this, plus and minus, then minus and plus while it is discharging. So now while it is discharging, what is the path? Instead of going to the lower group devices, now plus and minus, minus is directly connected to cathode, plus is directly connected to anode, therefore diode will be forward bias. Then the loop will be like this, output voltage will be 0, but current will freewheels through the freewheeling diode. Again, during negative off cycle, what will happen? It goes T2, again D, R and L, then goes to out. Again, here is diode is there now. For continuously diode will be there in the circuit itself. Then what will happen? Energy will be, this is minus, this is plus. Again, this diode will be forward bias. This loop will be repeated. Every instant, here what you will do? You just make it as a freewheeling diode. That's it. That is also fine. Some books they represented like that also. Anything is correct. So either you can use directly freewheeling diode across the load. We can made it short. That purpose itself of our freewheeling diode will not allow negative conduction. That's why that even if you not use freewheeling diode also, these lower group devices will act as a freewheeling diodes, will get 0 during that instance. Wherever negative has to come in the full controller case, that will be suppressed by the lower group devices is a diodes or directly can use it. But same thing, if arrangement is different, then the device conductions, waveform, everything is same. But only thing is, all the cases, one of the leg, this leg only the diodes, no leg act as a freewheeling diode. That's why you can see this duration freewheeling diode is going to conduct. Now you can measure T1 is conducting only this duration. But what about the D1 conducting here and here? So therefore, D1 is conducting more instants. T1 is conducting only pi minus alpha instant. But what about D1? D1 is conducting pi minus alpha also, D1 is there, and plus this duration is alpha instant also, D1 is there. Therefore what will happen? Totally pi it is conducting. And similarly if we take T2, it will conduct only pi minus alpha. And again, if we take D2, it will conduct, what will happen? Pi. So therefore, thyristors are conducting only pi minus alpha instant, but diodes are conducting pi instant. That means 180 degrees, this is conducting, this is 180 minus alpha, it is conducting. That's why devices are not in symmetrical. Thyristor durations are different, diode durations are different. That's why we call it as a asymmetrical configuration. So this is the way we can explain, or else we can use, I already said now, you can use directly as a freewheeling diode across the load. Now it is fine. So this way also correct. Any waveform you can give. Waveforms are, all the cases are same. Only different is diode. Whether we are using separate diode or inbuilt. This lower group also will act as a diodes. Is a freewheeling diodes. That's why again waveform is same. Whatever we are doing, this also we are doing simulation, no, in our lab. So this is the case. We'll explain, and once if this you can see the waveform again same, you are not getting any negative voltage, but current is there. Current is passes through the freewheeling diode. So now we'll stop this today's class, and I think today, and you can compare this waveform, and because of full control rectifier, positive and negative are getting, but semi control will give only positive voltage, because Vm by pi into 1 plus cos alpha, no, whatever alpha you keep 0, 90 or 180, maximum it will give 2 Vm by pi, both is same and gradually decreasing, and if it is 90 degrees will give Vm by pi, and if it is 180 degrees we will get it as a 0. So because cos 180 minus 1 minus 1 will be 0, resultant will be 0. So this is the comparison between semi converter and full converter. From this comparison it is clear that semi converter will give only first quadrant, because it will give only positive voltage, and full converter either positive or negative, depends upon your alpha. So that's the semi converter and full converters. And I think afternoon at 5 o'clock you have as a slip test one. For that there is a password, and anyone can call me. CR will call me, and I will give the password and write the first slip test exam. That's all. If you have any doubt, ask me. Otherwise, you can leave.